Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, good morning. Thank you for being there. It's a pleasure to me to introduce Cornelio Popea. He's finishing his PhD in the National University of Singapore under the advising of Professor Chin Wei Kan, and he studied in University Polytechnic of Bucharest. Okay, so that it looks as in Italian. So, and he made very interesting work on computing disjunctive fixed points. So today he's going to talk about this disjunctive invariant for modular static analysis. Thank you.
Thank you very much, Francesco, and thank you for allowing me to come here and visit. It's such a nice experience for me. My talk today is on how to use disjunctive invariants for modular static analysis, and this is joint work with my supervisor, Prof. Chin Wei Kan. I will start by giving a motivation on static analysis, which we all know by now. The goal is to analyze what programs will do without actually executing them, to discover interesting program properties, as well as detecting various program errors at compile time before they happen, which was the unfortunate case with these monitors in the airport, which encountered an error rather than showing gate and flight departure.
There was advertising on the right, so maybe it's advertising on the left. No.
Oh, right, yeah, it could happen. There have been many success stories in static analysis, and I list only two on this slide. One of them is the static analyzer Astre, built in the group of Patrick Guzot, which managed to prove the entire absence of runtime errors in a quite large flight control software on board of Airbus airplanes. And the second example is a checker built at Microsoft, the SPX, that is used for preventing buffer overflows in the huge code base of Microsoft products, which is over 10,000 lines of code.
So, have they actually stated that for the first one? I think they're usually very careful to say that there are no, they miss no errors, and everything that they have reported, and they have not reported any spurious warnings. But that, so they, right, so there could be errors that they have found later. Have they actually now said that there are no errors left?
I think you're right, it's more than something that can be said in 2 lines, so you have to be very careful about what errors you're saying that you removed. In general, it would be quite tough to be formally certain that everything is right in place. So with these successes, there are some less pleasant things. One example is that due to the global nature of the analysis in Astre, invariants may involve tens of thousands of variables, and in this case, the inspection of an alarm, of a simple alarm, could take several days by itself. And for the second case, for ESPX, the global analysis is complemented by some annotations written at the method boundary, which makes the analysis much more suitable for the kind of applications that is used, but it requires programmer to write quite a number of annotations, so there is a effort involved. And I know this conclusion sounds quite abrupt, but I would say that global reasoning about large programs still remains difficult despite these successes, and there is certain interest in looking at modular static analysis, how they could help. So modularity implies that there is a separate abstraction for each method, and method summaries are computed to concisely represent effects of the method invocation. For the code that is shown on the left part, we can think of the program as the entire box and of methods as the small yellow boxes. The global analysis would have to deal with invariants computed in the global scope of the program, while for the modular analysis, you would start, of course, like in the global analysis as well, you would start with a call graph and process it bottom up, and compute for the first function a summary, which is denoted by a function, by a phi formula and process the others one as well. Then the caller would be able to use the summary rather than performing the analysis for both the caller and the callee, and thus the analysis may have a smaller scope, a local scope. As well, there might be not a need to reanalyze a method in each of its call contexts because the summary can be reused. However, with these benefits, there comes the main difficulty, which is that you need to reason about symbolic inputs of the methods rather than fixed value parameters. So there is a need for a more complex domain, as well as the analysis could potentially be more expensive and less precise. There are lots of works in modular static analysis, and this slide gives a brief account of them, grouped depending on the abstract domains that are used. First, there are some general purpose interprocedural analysis, which started with the seminal works by Couzeau and Couzeau, as well as Charrier and Pnoeli in the 80s. Then Reps, Horvitz, and Sagiv showed how to perform precise interprocedural analysis for finite domains with distributive transfer functions. There have been a lot of interest in defining modular aliasing analysis, and more recently Greta Jorsch showed how to perform finite type state with aliasing. More closer to the focus of this talk are analyses that perform on numerical domains. They also are interested in getting precise analysis. By precision, they mean that very intuitively the modular analysis has some property related to the global analysis. It's able to discover a similar kind of invariant. But this can be guaranteed only under some restriction, like, for example, the conditionals that can be analyzed precisely are non-deterministic conditional. They are not able to take into account values of particular conditional test. So there have been works that deal with linear equalities domain, and Gulvani showed how to extend this also to uninterpreted functions. For a more precise and infinite height domain, like the polyhedral domain, there is some work which is mostly concerned with efficiency by Helmut Ziedel in ESOP 2007, where they used is a restriction of the polyhedron so that they can get operations that have polynomial complexity rather than exponential complexity. So our focus is also on the bottom part of the slide. We plan to adapt the polyhedron domain to make it more suitable for modular analysis, that is to allow it to capture both conjunctions but also disjunctions of linear invariants. And in this goal we are helped by the fact that the modular analyzer, as said before, requires an expressive abstract domain to reason about the symbolic inputs, but it also favors such an expensive analysis because with local scope you could hope to get more complex invariants than in the global approach. So my talk is divided roughly in two parts. First, I will talk about an abstract domain that involves disjunction and conjunction of linear inequalities, and then I will talk about a dual static analysis that is able to prove safety as well as find and confirm true bugs in programs when safety is not possible to prove. So the first part is on the disjunctive abstract domain. And on this slide I have again some related work, but this one is only about abstract domains where you have infinite height lattices, so the termination of the analysis is even more an issue. There have been some works by Couzeau and Halbach in the late 70s on conjunctive numerical abstract domains that are able to discover interval constraints as well as polyhedron constraint, both of them being linear inequalities. And Couzeau also showed how to extend this kind of analysis to a Powerset domain where disjunctions can be captured precisely. The problem with this extension is that in general it is exponential in complexity as compared to the conjunctive analysis. More recently there have been renewed interest in defining both precise but also efficient operators, widening and hulling, to deal with disjunctive domains. And for the works at the bottom, I will go into more details about how they compare with our work in the next slide. I will use a very simple example to show how our approach deals with this disjunctive fixed point analysis. This is a function MND that takes just one parameter x passed by reference. If x is negative, then the function is done, it returns. Otherwise, it decrements x by 1 and it calls itself recursively. So there is an obvious loop counterpart for this tail recursive function, but in our system we analyze loops as well as function in a similar way, so I wrote it as a tail recursive function. So our goal for this part is to compute a postcondition, and it's easy to see that this is roughly what we expect, that it's a disjunctive postcondition requiring that if x, the initial value of the parameter, is more than 0, then x prime, the value of x after the loop iterates and terminates, is unchanged, so we have x prime equal to x. And the second disjunct captures the fact that if x is positive, then it will be decremented and finally the latest value is 0. So for this simple example, our approach is, first we have some rules that derive a constraint abstraction from the code, and the constraint abstraction we can think of it as being kind of equivalent with the code, but the fixed point analysis will deal with this constraint abstraction. So let's try to read it. It's a function that takes two arguments, the initial value of x and the latest value of x, and the two branches from the original method are encoded as a disjunction. So we have the base case when the function terminates immediately, as well as the recursive case when x is positive. A local variable will take the value of x minus 1, and we have something that is a placeholder for the recursive call with a substitution, as we expect, from formal to actual arguments. So the value of x is replaced by x1, which is x minus 1 in fact. So this is a recursive constraint abstraction, and what we'll do is to derive a approximation for a fixed point for this constraint abstraction, and this will correspond to the postcondition that we are looking for. So we can reason about fixed points because from the way that they are constructed, constraint abstractions are monotone functions, and MND is such an example. Rather than having two parameters, we have one relation over both inputs and outputs, and this is denoted by phi. You can see it in the recursive call place over here appearing. So this is just a function which is monotone, and we want to compute approximation for the fixed point. The usual approach is to start from, first to choose an abstract domain, then to start from the bottom element, the least element of the domain, and continue to iterate until you reach a fixed point. So the intuition behind these steps is that the first step will represent the postcondition of the function only for one iteration, then the next step will represent the postcondition of the function for two iterations, and you will continue to do this, incorporating iteration by iteration. Ideally, you would reach a fixed point. This is an ascending chain, so each approximation is less and less precise, and for the particular domains that we are interested, those that are derived from the polyhedron, it's not guaranteed that this ascending chain will converge, so we will have to use some operators like those that were introduced by Couzeau and Halbach in the polyhedra analysis. This is one slide to see how the polyhedra analysis would work with these constraint abstractions. So we just start from the least element, as we said, and after some simplifications which are denoted by equal s here, we get the first formula. Then we can use this first formula and plug it right where the recursive call used to be, in the argument place. And for this closed formula, we have an existential quantifier. We can use a quantifier elimination package for linear inequalities. And we observe that for this we get a two disjunctive formula. So this is not directly representable in the polyhedra analysis. And what is used in this case is a Hull operator, the join of this abstract domain, which is able to obtain an approximation for this disjunction. Okay, so what this does is that it, geometrically speaking, you have a disjunction which each disjunct corresponds to a polyhedron. You want to draw a convex hull that covers both of them. It may involve some loss of precision, but it will allow you to represent this invariant in the conjunctive space. We can proceed to the next step, which quite similarly will reduce to this constraint, and here we can observe that if we continue to do this, because of the infinite height of the domain, there is a need to use the widening operator to ensure the convergence of this analysis. So,
in the abstraction to the hull, the row term disappears.
What happened here is that MND1 would be replaced with the formula computed in the previous step, in which you'd want to replace the formal arguments, which are x and x prime, with the actual arguments, which are x1 and x prime. So this is applied right when you have a function here. You can apply the substitution and get a formula in terms of x1 and x prime. And then the second disjunct becomes just a formula for which you can perform quantifier elimination. So going further, for the widening operator, it takes two arguments, which are, one of them is the operator from the previous step, MND2, as well as the operator from the current step, MND3, and it removes those conjuncts that do not allow this fixed point iteration to stabilize. So intuitively, this is the first constraint in this case. And after performing this widening, we can test to see whether a safe approximation for the fixed point was found. And this is the case. So this is the result of the conjunctive fixed point analysis, which roughly captures the information that the latest value of x is smaller than the initial value, which is to be expected because you decrement it on each step. And also the latest value of x is negative. So given this result from the conjunctive analysis, what we wanted is a little bit more precise result. And if we want to allow disjunctions in the fixed point and try to think about a similar ascending sequence to compute, the first problem with this naive derivation is that at each step we will accumulate more and more disjuncts, and it's not obvious how to bound this growth. Ideally, if we look at the disjuncts in this step, what we would want is that the first disjunct, which arises from the recursive case, is kept separate, while the other disjuncts are merged to give the result that is expected. But in general, for more complicated examples, the control flow will not be sufficient. So we need to look at the disjuncts itself and see which one are more suitable for combining. So our approach is to use a Powerset extension of a conjunctive domain where the number of disjuncts is syntactically bounded by a parameter m of the abstract domain. And the key problem is how to maintain precision, because if you are not careful about which disjuncts you merge, you may get less precise results. And also to ensure termination of the analysis with the use of the widening operator, which needs to be adapted for this abstract domain. Our solution is to use a so-called disjunct affinity, which tells you how suitable two disjuncts are to perform some particular abstract operations like hulling and widening, and thus allow those operators to be used in the disjunctive domain. So first, just some intuition about what an affinity measure, a good affinity measure, would look like. It should be able to quantify how precisely a disjunct, like phi1 or phi2, can be approximated when you perform the abstract operation, the hulling operation. So if we look at this example on the slide, we have the disjunct, which is represented by this hashed area. And we need to find a way to see how much precision is lost when we apply the convex hull operator. And we will try to find a way to compare the disjunct with the hull. Also, we would ideally want to identify when we have a perfect match between the disjuncts. So in this case, we have so-called 100% of these two disjuncts for affinity. The reason is that whenever you apply the hull operator, there is no loss in precision. So you can do it without any penalty. There have been a measure proposed for a disjunctive numerical abstract domain discussed in SAS 2006 by Sriram Sankaranayan. He used a geometrical measure, which is the average Hausdorff distance. It's computed according to the formula on the table. What roughly the formula does is that given two polyhedron, you try to find the closest point from the rightmost polyhedron and the further point from the left polyhedron, and then compute the geometrical distance between them. And this should give you an intuition about how much area the hull will cover when you apply it. There are two problems which we may think of this heuristic. One is that for this simple example on the slide, we wouldn't expect this geometrical distance to be able to distinguish between the pairs of polyhedron. So ideally we would want the second pair to be hulled, but both pairs have similar geometrical distances. And the other one, which seems to be more troublesome, is the fact that the Hausdorff distance is in general quite complicated to compute. So what the authors proposed is to use a interval-based projection. So this makes it less appropriate for a relational domain. They used it for an interval-based domain where you have more information about constant bounds of the parameters, but in general it's not really meaningful to compute the distance between two completely symbolical formulas. Our proposal here is to use a so-called planar affinity, which tries to get a measure of how many constraints are preserved in the hulling process. So let's see how it works for this particular example. It is a fraction of all the constraints from phi 1 and phi 2, the two arguments. So in this case we have 4 constraints for each one of them. So we get a fraction of the 8 constraints, and a number of them are preserved in the hulling process, like the leftmost as well as the rightmost constraints. They subsume the result of the hull operation. So when you perform hulling, these are the 2 constraints that you will keep, but intuitively the other one will be lost in the process. For the rightmost pair of polyhedron, you can observe that much more constraints will be preserved, because practically the entire bound of this polyhedron will be preserved. So this will detect that the second pair has higher affinity, and ideally this is what you want to be careful of, not so much about the distance between the polyhedron, but about the constraints that you can keep when you perform this abstract operation. And this is quite suitable for relational domains because it doesn't need to compute, again, any measure of a geometrical distance, but how these constraints are preserved.
So what's happening when you have one of the bounds, so the polyhedra is not closed, so it goes to plus infinity? Something that goes.
Right. So in that case, what this operation is looking like is the syntactic form of the constraint. So when we have something like x more than the infinity, practically this constraint won't appear in the original formula. So it's like it's not preserved, or it is preserved. It's implicitly there. So after giving this intuition about the affinity, let's see how we can use it for hulling and widening processes. So for hulling, we would want to perform a so-called selective hulling. Given a number of disjuncts, n, we want to find those that are suited for hulling, but not to hull all of them, as in the conjunctive case. So we have a formula f in the DNF form, disjunctive normal form, and we want to find the most affine disjuncts for hulling according to the affinity measure, and be sure that we don't exceed a given bound on the abstract domain. The way this is implemented is shown on this slide with an example from the previous slide. So at some iteration, MND3, we have a formula that corresponds to 3 disjuncts. And we denote this by F1, F2, and F3. We need to compute pairwise affinity between each F1, F2, F2, F3, and so on. So all these affinities are arranged in a matrix, affinity hull matrix. And we need to compute only the upper diagonal of the matrix because the affinity is commutative. Whether you compute affinity of F1, F2 or F2, F1 will give you the same result. So in this case, the last 2 constraints are perfectly suited for hulling because you don't lose any information in the integer domain when you hull them. and the others are less suitable. So practically what this will make the hull operator do is that it is distributed inside a disjunction. So originally it takes a 3 disjunct formula, and then it chooses the pair F2 and F3 to be hulled, and it uses the operator on the conjunctive domain. So we are left with these 2 disjuncts over here. Quite similarly, we can apply this idea to define a widening on the Powerset domain, which was not done by the other paper. So in this case, we have the formula F1 at the previous step as well as the formula F2 at the current step. And we want to find similarly pairs of related disjuncts from the 2 formulas based on the affinity and compute widening on the conjunctive domain for each pair chosen, the I, j. In the end, the result of the widening, which has the underscore m, so this is the Powerset widening operator, will be a disjunct of the widenings from the conjunctive domain. There are some related work here as well. So Roberto Baniara proposed a general framework for performing Powerset widenings. They use a connector to combine elements from F2, the current step, so that each connected element approximates some element from F1. But they don't give any specific means of computing this connector. In this case, we can think about the affinity of a mean to find those disjuncts that you really want to combine and widen against the original formula. Also, work by Bhargav Gulavani and Sriram Rajamani in TACAS involved the specification of a connector. But what they did is that they rely on some ability that is not available for the polyhedral domain. So they also compute all the pairwise combination between the previous step and the current step. In the end, they compare the results and try to choose the minimal, the most precise result. But you cannot simply compare the results in the set of polyhedra because this is not totally ordered. So in general, you don't have a perfect solution. This is, again, for the simple example, how the widening would perform. So we have MND3, which is a previous step, as well as MND4, which are denoted as D1 or D2 and D1 or E2. We again compute a matrix. Note that the affinity is an high order operator, so it needs to know what abstract operator you want to approximate. So the computation is different whether you want to approximate hulling or widening. And these are the results that are computed. So if you choose to widen D1 with E1, there is no loss in precision. That's intuitively because you have the same formula, so the widening will give you back the same result. If you choose to widen D2 with E2, you get some measure here as well as for the other pairings. Of course, things get more complicated when you have a higher bound for the abstract domain, because this involves at least a quadratic complexity, because you have to combine pairwise check. There are various improvements that you can make depending on the precision or efficiency that you are looking for. So the widening operator is again distributed inside the disjunction, and in this case you will perform widening between D1 E1 and between D2 A2 and get this result. This is the precise result that we are looking for, again, for this very simple example. So I will just summarize it on this slide, just to compare it to the conjunctive fixed point analysis that we've seen before. We again start from the same list element of the domain. For the next iteration, we have a 2 disjunctive formula, which if we choose the number of disjuncts to be 2, then there is no approximation involved. We can maintain this disjunct. For the next step, we get a 3 disjunct formula, which this time needs to be approximated. And the approximation is done precisely, so this is what we get. Again, the lattice has infinite height, so there is a need to use the widening operator as in the previous slide. And the result satisfies the condition for a post-fixed point, so this is the result that we get from the conjunctive fixed point analysis in this case. Yes?
For your hull 2 operation, then you select, you select between the three disjuncts so that you get two disjuncts as output. Right? So that's when you use the affinity or the measure.
Yes. Yeah. So that's the first place where it's used to decide that the second and third disjunct are more affine. So you want to combine these. And the second place that you'll use it is in the widening. Here you have two disjuncts in the first argument, two disjuncts in the second argument, and you decide that the first are those that you want to combine.
So you cannot do it syntactically in a way because even the form of your fixed point equation was the base case or the recursive case. So this the other two are coming from the recursive case. You can just say, okay, let's put the recursive case together. So is there a case in which you choose the new entity is the base case and the example you try the disjuncts from the base case some one of the next steps, or you are always joining stuff that are in the recursive case?
Yeah, yes, there are more complicated cases. Like this case could most likely be handled by a trace partitioning, which looks only at the control flow tokens. So let's say you want to keep the base case separate and all the recursive case you want to merge together. So this is very easy to handle. But one of the examples where this won't work is the one which we borrowed from your paper in A+, where what happens is that there are multiple passes through the loop. And it's not that you want to keep all the disjuncts that come from the then branch and all the disjuncts that come from the else branch. There is a more complicated interplay. So you can't really judge only on the control flow. You need to look at the disjuncts and decide semantically based on their representation which are more suited or less suited for Halling. But this example is inherently very simple, so it can be handled by a simple approach. These are just some simple examples for programs like algorithms like binary search, merge sort, or quicksort, as well as some larger numerical libraries like fast Fourier transform or LU decomposition. What we wanted here is to see what kind of postconditions we compute when we increase the number of disjuncts from 1 to 5. The effort of computation is quantified by how big is the program, which is given here in number of lines of code, but as well as how many recursive constraints you have. So this corresponds to the loop, they correspond to the recursive function. This is where the fixed point analysis will have to work on. This is the timing for the conjunctive case. And for the disjunctive case, there are two measures. If we look at m equal to 2, we'll see some timing that usually increases from the previous step, as well as a number of postconditions that are more precise than in the previous step. So for example, for merge sort, we can see that out of the 3 recursive functions, 3 of them are more precise, but at the expense of the increase in time from 1 second to 3 seconds. Then as we go to m equal to 3, we see that out of those 3 recursive functions, one of them has a more precise fixed point, again at some increase in time. And this happens in this case to m equal to 5. For those cases where we have a minus, this means there is no increase in precision, and consequently there is no increase in time. There's the other thing, which is you have to decide on what parameter you want to use for the abstract domain, how many disjuncts to use. There are various heuristics. The one that we use, which is quite useful and it automatically derives a good bound, is that you unroll the recursive definition a number of times and then measure how many disjuncts are different. And this is the bound that you're going to use for the parameter. In practice, we found that the bound between 3 and 5 is quite precise and not expensive, so it works quite well in practice. And we also found that for some cases we are able to derive quite precise postcondition. Like, for example, for merge sort, for m equal to 5, the postcondition that we derive, which is obviously an over-approximation for the reachable states, is also good enough to derive sufficient preconditions as well and prove all the array bound checks in the programs. But that's not the case for the lower parameters. So in this case, you would need 5 disjunctive domain. So with this, I conclude the first part. I'll talk a little bit about how to do dual static analysis. And the motivation behind this is that a static analyzer inherently will raise some false positives when it has to prove safety, and our goal is to extend the static analyzer to be able to prove safety but also to discover and confirm some true bugs. And what we want to do is to be based only on over-approximation, so that we have a simple extension from the previous analysis. And the way we proceeded is by performing two dual analyses that are computed concurrently over the program. This is the same example that we've seen before. It's just augmented to have an array access. So the function takes now two parameters, the array and the variable x, which is decremented until it gets to 0, and we have an array access over here. Ideally, we'd want to prove the assertion that x is a correct index for the array, so that it's bigger than 0 and smaller than a, where a here denotes the length of the array in the assertion. So for these programs, we can think about the concrete semantics, which correspond to three possible outcomes for a program execution. We can have executions that terminate successfully, which is no assertion is failed. We can have some executions that are unsafe due to some failed assertion, and also we may have non-terminating execution. So each one of them is denoted by small letters, OK, error, and loop. And what we want to do is to compute over approximations for inputs that lead to all the possible safe execution as well as all the possible unsafe executions. Because of the approximation in the analysis, what we will get is, if we think about this as being the input domain, we get a partitioning of the input domain. So some inputs will be in this circle, in the all possible safe execution, some other will be in the unsafe execution. And whenever we have an intersection, this means that for this input, we don't really know whether it's going to be a safe execution or unsafe execution. So this is where the imprecision is. And what can we do with it is we may hope to compute a condition, so-called a never bug condition, by taking the intersection between the OK input partitioning as well as the complement of the error input partitioning. So in this case, we get this never bug condition. Note that in the other part, we are guaranteed to have all the red inputs, all those that can lead to bugs. So in this part, it's a guarantee that we will not have any error execution. And we can conclude that any input satisfying this condition is guaranteed to lead either to OK or to loop. So this is somehow equivalent to a partial correctness proof. For these inputs, the program may not terminate, but if it does, it will surely not exercise any assertion failure. The second condition that we can compute is a must-bug condition, which is the intersection between the complement of OK as well as the error condition. So what we get is this part where we are guaranteed that there won't be any successful execution. However, we may have execution that lead either to an assertion failed, error, or to a non-termination. And we call this a bug because the non-termination is also a kind of execution that you don't want to happen to your program. So it's something that you have to be careful. So this is called a must bug for this reason. And the third partitioning that we have in this appears in the middle. In this case, the intersection between OK and error, there is nothing that we can say about those inputs. They may either lead to OK, error, or loop. How does it work for our case, and how can we use the previous fixed point analysis? So for the function that we had, we again just added this array access, and we can similarly derive a constraint abstraction from the code. The way this is different is that it takes one other parameter, the length of the array, and we have the base case which is unchanged. For the recursive case, we add the fact that the assertion may be satisfied, which is x being positive and smaller than the length of the array. So for this constraint abstraction, we will get a similar constraint abstraction meant to approximate the unsafe execution. So in this case, this error takes as parameters the inputs a and x, and it tells us how can you reach an error, which is the error is reachable only if x is positive, because if it's negative, there's no error on the base case. But if it is positive and you get this condition, either x is negative or x is bigger than the length of the array, this means that you will have an error on the first recursive call. Either you have this, or the assertion is satisfied, and you go into the recursive case, and you may encounter an error in the recursive case. So both these constraint abstractions can... Okay, there's the observation that in this case, the two constraint abstractions are totally independent, because this is a recursive function. But for a general recursive function, the error constraint abstraction may depend on OK. So you will have to compute both fixed points at the same time. This is not an issue, but it shows how you can reuse the information that is computed by one in the other computation. So for these two constraint abstraction, we can again perform fixed point approximation, and we get to two results using exactly the same process that we've seen before. So intuitively for the OK, what's this information is that if x is negative, we have no change in the parameter, which is what we know. And if x is in between 1 and a, the latest value of x will be 0. We also have some information about when an error may be reachable, when x is positive and when x is bigger than a. So there is no certain fact that if this condition is satisfied, we get an error. It's just an over-approximation. But for this particular case, the two formulas are precise, which means there is no intersection between the OK and the error outcomes. So practically when you compute the mass bug and the never bug, you will get exactly these formulas, and you are guaranteed to hit the bug or to have a successful execution. And two things that we can use to improve the analysis. One is to report where an error may occur. So in this case, for this example, we have a function foo that have an error here that is hit if x is equal to y. And we have another function that calls this function twice. And these labels are inserted automatically by the analyzer. So here it calls it with arguments x and x plus 1 and x and 3. So the modular analysis will compute a summary for this case, which says that the error is reachable, may reachable if you get x equal to y. And using this information, we can compute the summary for the second function, which mentioned that the error that is reachable by following the label L1 and L3 is false. So if we look, it's corresponding to the first call. So if we come from here, because the arguments are x and x plus 1, there is no possibility that they are equal. So the error is unreachable. For the second case, we get the condition x equal to 3, meaning that if the argument to this function is 3, then the arguments are equal, so we get a satisfied test and we will hit the error. So again, these are over-approximation, but you can easily compute the under-approximation from them and get a certainty of a bug or a certainty of a proof of safety.
In your OK things there,
yes.
It's a not equal sign.
Oh yes, it's barely visible. It's not equal.
And same thing up above, right?
Yes. One other thing that we can use this analysis is to detect some non-termination cases, which is that, of course, there are three possible concrete executions. Some of them are OK, some of them are errors, and there are some non-terminating cases. But we don't have a way to approximate which are the terminating cases. What we do have is that any input that is outside of these two circles, it's guaranteed not to lead to OK, not to lead to error, so it can only be non-terminating. So the part that is outside in the input partitioning, which we call a loop condition, an input that satisfies this condition is guaranteed to lead to non-termination. And this is a simple example that shows a non-termination bug. This is a function that has two local variables, x and y, initialized to 0. And this is a loop that continuously adds 0 to 0, so it will not terminate. And because it doesn't terminate, it won't hit the bug that is coming afterwards. This is an example from the Synergy paper on the software model checker. How the analysis will proceed here is that first we compute a summary for the loop. And in this case, we have the fact that we may have a successful execution if either x is negative or y is negative. and the error outcome is false because there's no error inside the loop. So the complement of this formula is only going to lead to non-termination, which is when x is positive and y is positive, you get a non-termination behavior for the loop. And when we use this summary in the method, what we get is the fact that there is no possibility for a successful execution. It's a certain fact that, this is a true formula for the loop at label L5, denoting this while loop, and the error in the end is unreachable. So by this we can conclude that we surely have a non-termination bug for the function. I will describe a little bit about the prototype implementation for this analysis, which is something that we call dualizer. It is written in the functional language Haskell. We use an efficient Presburger solver built by William Pugh, the omega calculator, on top of which there is a disjunctive fixed point analyzer. The objectives are to prove program safety as well as confirm true bugs when this is possible. And the programs are some small algorithms that we've seen before, like queens or quicksort, as well as some numerical benchmarks. The one tool that I could get my hands on and try to see how these programs are analyzed is BLAST. And this shows two tables. One of them is checking whether we can prove safety for the correct programs. And it has two columns. This proved is a star when it can't be proven safe, and there's a check when it can be proved safe with the time that corresponds to it. Of course, BLAST is not the best tool to use for this kind of programs. One reason is that it uses difference constraints rather than more expensive polyhedral constraints. And it also treats the division operator as an uninterpreted function. So for example, the binary search program where you have a division by 2, BLAST is helpless there. It can't really capture the result. So that's the reason why it failed to prove safety for some of the cases. Dualizer was able to prove safety with the exception of the Sentinel program, where we need to get a complicated property over the array contents, as well for Limpact benchmark for the same reason. We need to capture some property on the array elements. Timing-wise, my implementation is not too efficient, but for some cases the programs are really complicated, so it takes some time to chew all the polyhedron constraints in the fixed point. However, from the BLAST experiments, there is a shortcoming, which is that even when you feed it a correct program, BLAST will tell you that you have an error, but it won't give any indication whether it's a true error or false positive. So for this reason, when I run the bubble sort, for example, the correct bubble sort or a faulty bubble sort, I get the same message from BLAST. It can't tell what you get. But for some programs, we can discover some true bugs using dualizer, so it can guarantee that they are must bugs. And the timing roughly is increased from the other side, because here we need to use the precise error tracing in order to say that the bug that we found is at this label precisely. For the safety, you don't usually require that. If all the checks are proven, you don't need the precise error tracing. This is an account of some small examples from the Synergy paper by Gulavani, Thomas Hensinger, and Sriram Jamani in FSC. They use some small but challenging examples for model checking and analysis. Synergy in itself is a software model checker which is extended with a testing module. And for these examples, it's able to discover true bugs denoted by capital bug. It's able to prove that programs are safe, or it can time out during the refinement loop because it continues to refine the predicate abstraction, and if it can't find the right predicate abstraction, it may continue to do so. So for the examples that they had, Synergy was able to find a bug in this case, prove it safe, and for the last case, which is the one that you saw on the slide, it's aborting because of the refinement loop. And we were able to do as well as Synergy here by finding the must bugs for the faulty cases, as well as proving non-termination for the last case. there's also some experiments that I quite preliminary, which is I've tried a few programs for the Verisec suite of programs. They have some test cases which are actual vulnerability from CVE database as well as corrected version of these vulnerabilities. So model checkers would either want to find the bugs or to prove the safety for this kind of programs. And despite the simple analysis behind Dualizer, we were surprised to find 2 unknown bugs to the developers in the corrected test cases. So again, these programs are small, but the bugs are not entirely trivial. So we could find a off by 1 buffer error in this test case, and as well as a non-termination bug in the Samba test case. I will just have some concluding remarks, which is that our goal was to improve modular analysis by using disjunctive invariants. And we did this by using an affinity measure, which allowed us to raise the Halling and the widening operators from the conjunctive to the disjunctive domains. By using the dual analysis, we can also derive preconditions for the methods, complementing the post-condition derivation that I showed you on the first part of the presentation. And the dual analysis can be used to prove safety as well as find some bugs in the program. As future work, we want to adapt the affinity and the disjunctive fixed point analysis to weakly relational abstract domains like the octagon domain. It should work theoretically, so the affinity can predict very well which octagon constraints are suited for Halling, as well as develop and make it available for others to have a parametric fixed point analyzer. Currently it's parametric in the heuristic that you use, whether you're using the Hausdorff heuristic or whether you're using the affinity, but it could be parametric in terms of the abstract domain as well, so that you can use it for interval, octagon, or polyhedral domains. So this concludes my talk, and if you have any questions, I'll be very happy to try to answer them.
So I have a few questions, but first one, I guess, is in one of the examples you did 2 steps of Halling and then 1 step of widening.
Yes.
And I was wondering how you decide when to do the widening. Do you detect that this is going to go on forever, so I better do a widening now, or is there something else?
So if we just go on to recall this example, let me see. It's this example, right? What's happening here is that you start widening from the 3rd step. One thing that is usually known is that as you delay widening, you may get an increase in precision. How much to delay it? It's a heuristic, so you won't know what is the best result. In this case, yes, what's really happening is that you unroll the recursive definition 3 times, then you count how many disjuncts you have which are not 100% affine. And this is a good indication about what parameter you want to use for the abstract domain. Like in this case, you will only get 2, because when you look at this tree, the 2 are perfectly affine, so there is no problem, and then you use 2 for the abstract domain. You can change the heuristic as well, but this is the one that I've used. And then you probably will do widening in the 3rd step. You can apply widening repeatedly, and again, there are many factors that you can allow freely for this fixed point analysis. I should add that I have a web demo for this fixed point calculator, which really allows you to apply this operation like Halling and widening interactively. So you just plug in there recursive constraint abstraction, and you say, okay, what if I iterate 3 times and I apply widening here? What do I get? So you can easily play with various strategies and see, for example, that you may need to apply widening repeatedly or delay it or something like that.
Is there a question? Can you also? You talked about applying these techniques also to operators to recover precision, so for instance to narrowing of things like this. So maybe with polyhedral you don't need narrowing, but maybe widening can introduce several other disjuncts, and then you choose which one to use. But here you are recalling precision, so it's quite good thought about it.
The observation that you said is quite right, which is for these examples I didn't really use narrowing. I try to see whether it improves the precision, but it usually doesn't. I don't have a complete test for all the programs. What I wanted to test is also in how many cases you get a fixed point, in how many cases you only have an approximation for a fixed point. So I didn't use it for narrowing, but I think it would be certainly very interesting to do so.
Okay. And then another question about your disjuncts. You are not really forced to have all the elements of the disjuncts to belong to the same abstract domain, isn't it? You can have something comes from polyhedral, something else comes from octagons or pentagons and things. Have you thought about it? So for instance, more ways. Just saying something begins too complex, too expensive, and then let's see which
the one thing
we
that
keep together by another abstract domain, so that you can approximate with a weaker abstract domain and recover a lot of time, essentially.
I see. The one thing that we use it for is that really the constraints that we have are not entirely integer constraints. We also have Boolean constraints. So there, really the affinity is a combination of the affinity on the polyhedral domain and on the Boolean domain. And because the Boolean domain is very precise, you may want to consider that. So when you combine the two affinities, you'd really want to keep the Boolean constraints more importantly than the polyhedral constraints. So you can give different priorities, and so that would be one way to combine for two domains. Another heuristic which we thought it would be very useful is to give priorities to the variables that are involved. In the sense that for the parameters, you are really interested in the constraints that involve parameters, but not so in the local variables. So then it doesn't really matter that you have 10 constraints and then you preserve 3, but it may matter that those 3 are more important than the others. But this is something that I haven't implemented. It's only the one with the Booleans that have really used it.
Thank you.
Thank you.